Dear students, you all must be familiar with the importance of water in everyday life. You all know that water is essential to all forms of life. This essentiality is beyond question for organisms and consequently life processes that exist on the earth. It is common to assume that water is a typical liquid, much like any other liquid. But in fact, virtually every physical and chemical property is unusual regarding water when we compare it with other liquids. And it is these unique differences which make water essential to life. In this module, we will discuss each and every property in detail. Although water can take various forms, but we are generally most familiar with its liquid form or liquid state. Water is polar in nature. Now, what do we mean by polarity? There is charge difference between hydrogen and oxygen due to their difference in electronegativity. Due to this polarity, there is extensive intermolecular hydrogen bonding in water, and as a result of this, water is a liquid at room temperature and atmospheric pressure. Water molecule is bent in shape, and there is a partial negative charge on oxygen as it is more electronegative, and hydrogen has a partial positive charge due to its lower electronegativity. We will study about the nature of the chemical bond in water molecule. In water, atoms of oxygen and hydrogen are bonded by a covalent bond. We will also study about properties like heat capacity, surface tension, and density of water in detail. Now let us define a few of these terms. What is heat capacity? It's the amount of heat that must be absorbed or evolved to change the temperature of 1 gram of a substance by 1 degree Celsius. Water is known to have a high specific heat capacity and high enthalpy of vaporization. This is basically due to the extensive intermolecular hydrogen bonding in water. These properties allow water to moderate the Earth's climate by buffering large fluctuations in temperature. On the other hand, water has a very high surface tension. This is mainly due to the cohesive forces among the liquid molecules. The spherical shape of water droplets is attributed to surface tension. In this module, we will study this in detail. For water, as temperature decreases, density also decreases. This is something anomalous. This unusual thermal expansion is a result of the strong orientation dependent intermolecular hydrogen bonding. These properties of water have important consequences in its role in the Earth's ecosystem. The temperature of water accumulated at the bottom of lakes is different from its temperature in the atmosphere. This feature becomes very important because this is the essential feature which supports aquatic life. Water is known to be a universal solvent because it can dissolve any ionic or polar substance. In this module, we will also discuss about the different isotopes of water. You are familiar with the isotopes of hydrogen and oxygen. The 3 isotopes of hydrogen are H1, the most common one, H2 called deuterium, and H3 called tritium, while the important 2 isotopes of oxygen are O16 and O7. These different isotopes of hydrogen and oxygen result in the formation of different isotopes of water. The most common among these contain H1 and O16, and it is this water which is a necessary condition for existence of life on Earth. Now let us discuss this with the help of some graphics and visuals. This is the phase diagram of water, and this explains all the phases or the states of water. We are all familiar with the three states: solid, liquid and gas. Now as you can see here, at and above the critical temperature, that is 647 Kelvin, and critical pressure, that is 2200.064 megapascal, the liquid and gaseous phases of water merge to give a homogeneous fluid. Naturally occurring supercritical water is found, and where is it found? In the hottest parts of deep water hydrothermal vents, where volcanic activities heat water to its critical temperature and the crushing weights bring about the critical pressure. Supercritical water is expected to be present in any region having volcanic activity. Oceans produce it below a depth of 2.25 km. The temperature and pressure at which solid, liquid and gaseous water coexist in equilibrium with each other is called the triple point of water. And this point is used to define the units of temperature. The triple point of water is at a temperature of 273.16 Kelvin and at a pressure of 611.73 pascals. Now look at the diagram. The y-axis represents pressure in pascals. The x-axis represents temperature in Kelvin. S stands for solid, L for liquid, and V for vapor. Cp stands for critical point. And last and most important is Tp, which represents the triple point of water. As we had seen earlier, there are several isotopes of hydrogen and oxygen, and these give rise to different isotopes of water. Existence of 3 isotopes of hydrogen, H1, H2, H3, and 3 isotopes of oxygen, O16, O17 and O18, imply that water is a mixture of several isotopes, and each isotope differs from the other in hydrological, radioactive and biological properties. The most common form of water contains H1 and O16, and this is the form that is a necessary condition for existence of life on Earth. In fact, some of the other isotopes do not support life. They may decelerate chemical responses, they may be toxic and inert. There are some important physico-chemical properties of water which you can see in the table here. We'll discuss each of these properties and we'll explain why they are important. Now let us start with density. On cooling, water contracts until it reaches 4 degrees Celsius or 277 K. Why is it important? Small solid objects float on liquid water. Icebergs float in the big water bodies, and aquatic animals can live in the unfrozen water below. Freezing and boiling point. Pure water boils at 100 degrees Celsius, that is 373 Kelvin, and freezes at 0 degrees Celsius, that is 273 Kelvin. What is the importance of this? The high boiling point of water and the low freezing point ensures a slightly long temperature range in which water can exist in liquid form on the Earth's surface. Now, heat capacity or specific heat. Water has unusually high specific heat. In fact, it is highest after ammonia. Why is this important? This property helps water to moderate the temperature on the Earth by preventing extreme fluctuations. Thus, organisms and geographic regions are stabilized. Now, let us consider heat of evaporation or heat of vaporization. This is high for water. Again, the importance. It balances the difference in atmospheric temperature and humidity. Surface tension, very, very important property. Water has the second highest surface tension. Highest is with mercury, water is the second. And this regulates the movement of nutrients in the body and helps in the transport of water from the roots to leaves in plants. And you know, plants are the only substances that manufacture food. We all depend on plants. So this travel of nutrients is very important. Now, water is an universal solvent. Why? It is polar. It has a high dielectric constant. And what is the importance? Almost all ionic compounds dissolve in water, and water helps in transfer of dissolved substances in biological systems. Now, this table shows the physical parameters of water. We've already discussed about the importance of these parameters. So, in this table, all the values are given. For example, the boiling point of water, 100 degrees Celsius or 373 Kelvin. Freezing point, 0 degrees Celsius or 273 Kelvin. The maximum density of water is at 4 degrees Celsius, we had discussed, more accurately at 3.98 degrees Celsius, that is 999.97 kilogram per meter cube. The viscosity of water at 25 degrees Celsius is 0.889 meter Newton second per meter squared. The surface tension of water at 25 degrees Celsius is 72 mN per meter. The heat capacity at 25 degrees Celsius is 4.1796 kilojoule per kg Kelvin. The enthalpy of evaporation is 40.63 kilojoule per mole, and the enthalpy of fusion is 6.013 kilojoule per mole. The dielectric constant at 25 degrees Celsius is 78.40, and it is this high dielectric constant which enables water to dissolve ionic solutes. The electrical conductivity at 25 degrees Celsius is 8 microsecond per meter, and its refractive index at 25 degrees Celsius is 1.333. The thermal conductivity is 0.608 W per mK. Let us now understand the biogeochemical cycle. In order to maintain the biosphere and thus life, the chemical elements like carbon, oxygen, nitrogen, etc. must be recycled so that they could be used again. The distribution of elements in atmosphere, lithosphere and hydrosphere depends on the movement of chemical substances from one segment to another. The cycling of these elements makes the supply of nutrients possible in different environmental segments. These movements of nutrients are natural and hence prevents the accumulation of various elements in forms, quantities and locations that are harmful to life. This transfer of elements between atmosphere, hydrosphere and lithosphere is called geochemical cycle. In this cycle, interchange of nutrients occur among the abiotic, that is non-living components, and biotic community, that is the living components. In geochemical cycles, the transfer of elements can be described as movements of elements from a reservoir. Now, what is a reservoir? Where a material is concentrated to various other locations and finally back to the reservoir. The quantitative estimates of geochemical cycles are made from both the amount of elements in each reservoir and the flux between the reservoirs. The quantity of material passing from one pool to another per unit time and per unit area or volume is called flux rate. Now, each geochemical cycle is a model which explains the movement of a chemical or its compound in different segments of the environment. Many types of chemical reactions occur in these geochemical cycles, and the presence or absence of any component influences the chemical reactions occurring in geochemical cycles. Most of the reactions can also be affected by biological activities. If they are also considered, then the geochemical processes are called biogeochemical processes or cycles. Geochemical cycles are generally element specific, whereas a biogeochemical cycle is specific to those elements that are key participants in biotic processes. Biogeochemical cycles can be defined as the cycling of matter involving biological, chemical, and geological processes and phenomena. On the basis of movement of elements, it is classified as a gaseous cycle and sedimentary cycle. In gaseous cycle, as the name indicates, elements move through the atmosphere. The main reservoirs are the atmosphere and the ocean. An example is a carbon cycle. And sedimentary cycle involves the movement of elements from land to water and then to sediment. The main reservoirs here are the soil and sedimentary rocks. An example is phosphorus cycle. Now let us understand the hydrological cycle in detail. Most of the water of the world is found in oceans. This is about 97%. But this water is not very useful. Why? Because of its high salt content, and it can't be used for municipal, agricultural, or most industrial needs. Water serves as a pool for many dissolved and suspended materials. It is a vital component for all living organisms and for various biochemical processes. In water cycle, water interconverts in all the three states, that is liquid form, vapor and solid form. The water cycle is a key environmental dynamic for all types of processes: physical, chemical and biological, and had been in existence ever since oceans came into being. That is, more than 2 billion years ago. The movement of water on the Earth's surface and through the atmosphere is known as hydrologic cycle. The water cycle can be of two types, either a long cycle or various short cycles. Now, what do we mean by this? Short cycle. It involves only evaporation and immediate condensation and so on. The reservoir for short cycle could be any water body. And what is a long cycle? It involves various processes like evaporation, condensation, transpiration, infiltration, interception, runoff, stream off, and subsurface flow. The details of water cycles are now being discussed. Water reaches the atmosphere from the Earth's surface in the vapor form through evaporation, and these vapors get condensed and form clouds. The water then returns to the Earth in the form of rain. The reservoirs of water cycle are atmosphere, ocean, lake, and rivers, etc. Evaporation is the process where water from the sea, rivers, and lakes is converted into water vapors in the atmosphere. Water vapor in the atmosphere is called humidity. The water vapors tend to condense around minute particles called nuclei, which have been suspended in the atmosphere. These nuclei generally are dust particles, smoke, volcanic ash, or maybe any organic material. This transformation of water vapors to small droplets depends on how warm the water is and how much water vapor or moisture the air contains. Initially, due to small size, these droplets remain in the atmosphere as clouds. Cloud formation starts in the atmosphere when the moisture content of air gets close to the maximum possible amount. Finally, these vapors form precipitation. By the process of precipitation, the water comes to the water bodies and thus comes back or returns to the earth from the atmosphere. The phenomenon by which water evaporates from the surface of leaves is called transpiration. Infiltration depends on the soil type, type of vegetation, rock type, and whether the soil is already saturated by water. Greater the openings in the surface in the form of cracks, pores, or joints, more is the infiltration. The water that is not infiltrated is called surface runoff, which flows over the surface and gets discharged into streams. The term runoff water is generally used for the sum of surface water plus the groundwater that enters into stream. The figure shown here represents the different zones of groundwater. Let us now understand the term subsurface flow. Subsurface flow incorporates movements of water within the earth. When precipitation reaches the earth's surface, some of it will flow along the surface of the land as runoff, while the rest of it soaks into the soil and is called recharge. The water moves down through the soil until it reaches a depth where all the fractures, crevices, and pore spaces are saturated with water. This saturated zone is called an aquifer, and the water present here is called groundwater. The upper surface of a zone of saturation is called the water table. In other words, the water table is the first occurrence of groundwater. Above the water table is the zone of aeration. also called the unsaturated zone. Once again, the water has entered the aquifer, it doesn't stop there. The groundwater slowly moves through the spaces and cracks between the soil particles on its journey to lower elevations. This movement of water underground is called groundwater flow. The two figures shown here show the groundwater and water table and surface flow. There is some water in the zone of aeration, but it will not flow into a well. Therefore, successful wells need to be deeper than the water table. Eventually, after years of underground movement, the groundwater comes to a discharge area. Here it enters a lake or stream and becomes surface water. Thus, the water will once again be evaporated and the cycle will start again. Water has been transported through the water cycle for millions of years, and this cycle will continue forever. That is, in this cycle, water is constantly on the move. Now we've learnt a lot up to now. Let us summarize what we have learned. We have studied that water is the only substance that exists naturally on earth in all the three physical states of matter, gas, liquid and solid, and is always on the move among them. As you all know, pure water is colorless, odorless and tasteless. The physical and chemical properties of water are very unique, and this is the reason which makes it essential for the existence of life on earth. As water cools, it contracts until it reaches 4 degrees Celsius, then it expands until it freezes at 0 degrees Celsius. Water is regarded as an universal solvent. Hydrogen bonding, more specifically intermolecular hydrogen bonding, and polarity of water explain its unique solvent properties. Water has the second highest surface tension of all the common liquids. As we have seen earlier, only mercury has a higher value. The intermolecular forces between liquid molecules are responsible for surface tension. Water has high specific heat. It takes more energy to raise the temperature of 1 gram of water by 1 degree Celsius than in the case of any other liquid. Finally, the hydrological cycle or water cycle. This is a key environmental dynamic for all types of processes: physical, chemical and biological. The various stages of water cycle are, we've seen these, again I am repeating: evaporation, condensation, runoff, infiltration and subsurface flow.